and the endless darkness of the universe. There are places where time stops, where gravity crushes light itself, and where the laws of physics simply break apart. These are not stars, not planets, not even galaxies. They are the most powerful and terrifying objects in existence. They are black holes, the silent engines of the cosmos. Some are born from dying stars, others rule entire galaxies, and a few may be older than the universe itself. Today, we journey beyond the event horizon to uncover every kind of black hole that exists and what they reveal about the true nature of our universe. Stellar black holes. Stellar black holes are the graves of massive stars, the inevitable destiny of celestial giants that burn too brightly and too fast. When a star much heavier than our Sun exhausts its nuclear fuel, it can no longer hold back the relentless pull of gravity. Its core collapses inward with unimaginable force, crushing atoms, matter, and even light into a single point of infinite density known as a singularity. Around it forms the event horizon, the ultimate boundary beyond which nothing escapes, not even light. The energy from this collapse is so violent that it can trigger a supernova explosion, a flash of brilliance that briefly outshines entire galaxies before fading into darkness, leaving behind the silent core, a black hole born from death. Despite their destructive reputation, stellar black holes are among the most fascinating objects in the cosmos. They typically have between 3 to 20 times the mass of our Sun, compressed into a region only a few kilometers wide, smaller than a city, yet with gravity so intense that time itself slows near their edges. Matter falling toward them forms a spinning accretion disk, heated to millions of degrees as it spirals inward. This hot plasma emits X-rays that we can detect from Earth, allowing astronomers to identify where these invisible predators hide. Some stellar black holes exist in binary systems, locked in a deadly dance with a companion star feeding on it slowly, tearing off its outer layers and glowing fiercely in X-rays as they feast. Each stellar black hole is a frozen scar in space-time, marking the final breath of a massive star and the beginning of something timeless. Over billions of years, these black holes can drift through galaxies, merge with others, or sink into dense star clusters, sometimes growing into the seeds of supermassive black holes found at galactic centers. In their silent gravity, we see the ultimate cycle of creation and destruction, where a star's death gives birth to one of the most powerful and mysterious entities in existence: supermassive black holes. Supermassive black holes are the colossal rulers of the cosmos, sitting silently at the centers of most galaxies, including our own Milky Way. Unlike their smaller stellar cousins, these giants contain millions or even billions of solar masses, yet they occupy a space no larger than our solar system. Their origins remain one of the greatest mysteries in astrophysics. Scientists believe they may have formed when the universe was still young, either by the direct collapse of massive gas clouds or through the gradual merging and feeding of countless smaller black holes over billions of years. However they became the hearts around which galaxies formed, their gravity orchestrating the dance of billions of stars. Around these cosmic titans swirls an accretion disk of gas, dust, and sometimes entire stars, heated to extreme temperatures as it spirals inward at near-light speed. The energy released in this process can outshine entire galaxies, creating quasars, the brightest objects in the universe. Some supermassive black holes also unleash relativistic jets, narrow beams of plasma that blast out from their poles for thousands of light years, shaping galaxies and even influencing star formation. Their immense gravitational power bends space and time so severely that light itself struggles to escape their pull, leaving only the glowing halo of the accretion disk visible around a shadow of darkness. At the center of our Milky Way lies Sagittarius A*, a supermassive black hole with over 4 million times the mass of the Sun. Another, M87*, in the Virgo cluster, weighs nearly 6 billion suns, and its image, captured in 2019, gave humanity its first glimpse of a black hole's shadow. Despite their terrifying power, these giants are also cosmic architects, regulating how galaxies grow and evolve. When they feed, their energy blasts can slow down or stop star formation. When they rest, galaxies flourish. Supermassive black holes are not just destroyers, they are the silent sculptors of the universe, binding galaxies together and defining the grand structure of the cosmos itself. Intermediate mass black holes. Intermediate mass black holes are the missing link in the cosmic hierarchy, mysterious objects that bridge the gap between the small stellar black holes and the colossal supermassive ones. They are believed to have masses ranging from a few hundred to a few 100,000 suns, yet their existence has long been one of astronomy's biggest puzzles. For decades, scientists could only speculate whether such objects truly existed, as they were too massive to form from a single collapsing star, yet too small to be found at galactic centers like supermassive black holes. They may have formed through the merging of multiple stellar black holes within dense star clusters, or from the collapse of massive primordial gas clouds in the early universe, each theory offering a piece of the puzzle, but none yet complete. These black holes hide in the shadows, often residing within globular clusters or wandering through interstellar space, invisible unless something strays too close. When matter does fall into them, they produce X-ray emissions that give away their presence. One of the strongest candidates, known as HLX-1, lies in a galaxy called ESO 243-49, about 290 million light-years away. It emits powerful bursts of X-rays consistent with a black hole around 20,000 times the mass of the Sun, a perfect fit for the intermediate category. Another clue comes from the LIGO and Virgo gravitational wave detectors, which have picked up ripples in space-time from mergers that seem too massive to be stellar, yet too small to be supermassive, strong evidence that these elusive intermediates may indeed populate the cosmos. If confirmed, intermediate mass black holes could reveal how galaxies and their central giants were born. They might be the original seeds that merged and evolved into the supermassive black holes we see today. Their study could unlock the missing chapter in the story of cosmic evolution, the quiet era between the death of the first stars and the birth of galactic giants. For now, they remain like cosmic ghosts, glimpsed only through faint echoes and flashes, reminding us that even in the vastness of space, there are still layers of mystery waiting to be uncovered, the hidden steps between stars and galaxies themselves. Primordial black holes. Primordial black holes are perhaps the oldest and most mysterious type ever theorized relics from the very dawn of the universe. Unlike stellar or supermassive black holes, they were not born from dying stars or collapsing galaxies, but from the chaotic density fluctuations that occurred just moments after the Big Bang. In those first fractions of a second, the universe was a storm of unimaginable heat and energy, with matter compressed into a dense cosmic soup. If certain regions happened to be slightly denser than others, gravity could have caused them to collapse directly into black holes. These primordial black holes could range in size from microscopic, smaller than an atom, to thousands of times more massive than our Sun. They are the ancient fossils of the early cosmos, possibly older than the first galaxies or even the first light. Because of their diverse potential sizes, primordial black holes might behave in radically different ways. The smallest ones, with masses less than a mountain, could be evaporating right now through a process known as Hawking radiation, releasing bursts of high-energy particles as they fade from existence. Larger ones, however, might still survive today, quietly drifting through galaxies, invisible unless they interact with other matter. Some scientists believe that these black holes could even make up part of the mysterious dark matter that fills much of our universe, the unseen substance that holds galaxies together but cannot be directly observed. If true, it would mean that primordial black holes are not just ancient remnants, but a key to solving one of modern physics' greatest mysteries. Despite decades of searching, no primordial black hole has been directly detected. Yet their possible effects leave subtle hints, strange gravitational lensing events, unexpected microlensing patterns, or the absence of certain cosmic radiation signatures. Each piece of evidence adds weight to the theory that they may indeed exist, scattered throughout the universe like hidden time capsules from creation itself. To discover one would be to peer back into the very birth of time, to witness how gravity first sculpted the universe from chaos. Primordial black holes remind us that some mysteries aren't born in stars or galaxies, but in the very heartbeat of the universe's beginning. Microquantum black holes. Micro or quantum black holes are the smallest and most theoretical of all strange objects that exist more in the realm of quantum physics than in the vastness of space. Unlike their larger cousins, which form from collapsing stars or cosmic gas clouds, micro black holes are thought to arise from intense energy concentrations at incredibly small scales. Some scientists theorize that they could be created when subatomic particles collide with enough force to compress energy into an infinitesimal region of spacetime. This idea gained attention with experiments like those at the Large Hadron Collider, LHC, where particles are smashed together at near-light speeds. Though no micro black holes have been observed, their potential existence could connect the worlds of general relativity and quantum mechanics, the two great but currently incompatible theories of physics. A micro black hole would be unimaginably tiny, perhaps smaller than a proton, yet still possess a gravitational pull strong enough to trap light within its minuscule event horizon. However, according to Stephen Hawking's radiation theory, such a small black hole would evaporate almost instantly, releasing bursts of energy as it disappears. This radiation, known as Hawking radiation, is a key prediction that merges quantum theory with black hole physics. The smaller the black hole, the faster it evaporates, meaning that a micro black hole might only last for a fraction of a second before vanishing completely. These fleeting flashes could theoretically be detected as sudden bursts of high-energy particles, offering a glimpse into one of nature's most extreme quantum phenomena. If micro black holes do exist, they could unlock the secrets of the quantum structure of space-time itself. They might show that gravity becomes granular at subatomic scales, revealing a universe where space and time are not smooth, but made of discrete quantum bits. Some theories even suggest that micro black holes could be produced naturally by cosmic rays striking Earth's atmosphere, appearing and evaporating before they can cause any harm. Though still hypothetical, their discovery would revolutionize physics, proving that black holes are not just cosmic monsters, but also quantum gateways, connecting the largest scales of the universe to the tiniest realms of reality. Kerr-rotating black holes. Kerr black holes, also known as rotating black holes, are among the most fascinating and dynamic objects in the cosmos. Unlike the simpler, non-spinning Schwarzschild black holes, Kerr black holes are born with an incredible angular momentum, meaning they spin at tremendous speeds, sometimes close to the speed of light. When a massive star collapses into a black hole, any slight rotation it had is conserved and amplified as the star's mass compresses. This rotation drags the very fabric of space-time around it, twisting it into a whirlpool of gravity known as frame dragging. In a Kerr black hole, space and time no longer behave normally. Instead, they swirl around the black hole in a vortex, forcing everything nearby, even light, to rotate with it. Surrounding a Kerr black hole is a region called the ergosphere, a distorted area that lies just outside the event horizon. Inside the ergosphere, nothing can remain still. Space-time itself is being dragged so violently that every particle must spin in the direction of the black hole's rotation. However, unlike the event horizon, escape from the ergosphere is still possible. This strange region allows for one of the most extraordinary phenomena in physics, the Penrose process, through which energy can theoretically be extracted from a rotating black hole. If an object enters the ergosphere and splits, part of it can fall into the black hole while the other escapes with more energy than it had before. In theory, this makes Kerr black holes potential cosmic power generators, capable of releasing unimaginable amounts of energy from pure rotation. The rotation of a Kerr black hole also alters its shape. Instead of being perfectly spherical, it becomes flattened at the poles and bulged at the equator due to its spin. This rotation stabilizes the black hole and affects how matter behaves in its accretion disk. The faster it spins, the closer the disk can orbit before being swallowed, creating hotter, brighter emissions that astronomers can detect. Most black holes observed in the universe are believed to be Kerr-type because almost all stars spin before they die. The concept of a rotating black hole reveals that even in a realm dominated by gravity and darkness, motion and energy still persist, weaving the fabric of the universe into a swirling dance that never truly stands still. Charged Reisner-Nordstrom black holes. Charged black holes, scientifically known as Reisner-Nordstrom black holes, are a rare and exotic class of black holes that possess not only mass and gravity, but also an electric charge. In most realistic cosmic environments, black holes are expected to be electrically neutral, as any charge they gain quickly attracts opposite charges from surrounding matter, neutralizing them. However, in theory, if a black hole were isolated and managed to retain an electrical imbalance, it would become a charged black hole, a strange fusion of electromagnetism and gravity, two of the universe's fundamental forces. These black holes would warp both space-time and electromagnetic fields simultaneously, creating effects far more complex than those of ordinary black holes. The presence of charge dramatically changes a black hole's internal structure. Instead of a single event horizon like a normal Schwarzschild black hole, a charged black hole has two, an outer horizon and an inner horizon. Between these two boundaries lies a turbulent region where space-time behaves in unpredictable ways, where light paths twist, time reverses direction, and the laws of physics begin to blur. If the charge becomes extremely high, the two horizons can merge and eventually vanish, exposing the singularity itself. This state, called a naked singularity, is forbidden by most physical theories, as it would violate the cosmic censorship hypothesis, which insists that singularities must always be hidden from the universe by an event horizon. Yet, the possibility of such an object pushes scientists to question the ultimate limits of nature's laws. In reality, charged black holes may never truly exist on large cosmic scales, but their mathematical beauty makes them crucial to theoretical physics. They help scientists explore how electric fields interact with gravity and how energy might behave near the most extreme conditions in the universe. Some theories even suggest that small, primordial black holes could carry a stable electric charge, making them potential candidates for dark matter. The Reisner-Nordstrom black hole remains one of the most elegant and mind-bending solutions to Einstein's equations, a reminder that even in the depths of darkness, the universe hides intricate symmetries between light, charge, and gravity. Schwarzschild non-rotating black holes. Schwarzschild black holes are the simplest and purest form of all black holes, the classic version that most people imagine when they hear the term. They have mass but no spin and no electric charge, making them the most mathematically elegant solution to Einstein's equations of general relativity. Discovered by German physicist Karl Schwarzschild in 1916, just months after Einstein published his theory, this type of black hole represents the most basic way space-time can collapse under its own gravity. In a Schwarzschild black hole, everything is perfectly symmetrical. Matter falls evenly from all directions toward a central point of infinite density known as the singularity, where space and time effectively cease to exist. The defining boundary of a Schwarzschild black hole is the event horizon, a spherical surface marking the limit beyond which nothing can escape, not even light. For a black hole with the mass of our Sun, this horizon would be just 3 kilometers across. Yet within that tiny region, gravity is so powerful that time slows to a crawl for any observer approaching it. To an outside viewer, anything falling toward the event horizon would appear to freeze in time, fading slowly as its light redshifts into darkness. This illusion is one of the many strange predictions of relativity that come alive near a Schwarzschild black hole where time, light, and reality itself are distorted beyond human comprehension. Because they lack spin and charge, Schwarzschild black holes are often used as the benchmark model for understanding how all black holes behave. They reveal the raw geometry of space-time curvature without any additional complexities from rotation or electromagnetism. Many stellar black holes closely resemble this form if they lose their angular momentum over time. These non-rotating giants serve as a cosmic baseline, the pure gravity version of a black hole. They are the still, silent hearts of darkness that define the very concept of what a black hole is. A region where gravity reigns absolute, where time halts, and where the universe folds in upon itself in perfect, symmetrical silence. White holes. White holes are the theoretical opposites of black holes. Instead of swallowing everything, they expel matter and energy, allowing nothing to enter. In essence, a white hole is like a cosmic mirror image of a black hole. Where one pulls in everything, the other pushes everything away. According to Einstein's general relativity equations, if black holes exist as solutions to space-time curvature, then white holes are also mathematically possible. However, unlike black holes, there's no observational evidence that white holes actually exist. They are purely hypothetical, perhaps relics from the Big Bang or short-lived phases in the life cycle of black holes themselves. If real, they would be among the most exotic and short-lived objects in the universe, spewing out light, matter, and radiation before fading into nothingness. A white hole structure mirrors that of a black hole, with an event horizon that marks the boundary between inside and out. But instead of preventing escape, this horizon prevents entry. Nothing can cross inward. Every particle, photon, or wave that approaches is violently repelled. Some physicists believe that a white hole might form when a black hole dies. As it evaporates through Hawking radiation, it could release all the information and matter it once consumed, reversing its flow of time. This idea links to the concept of wormholes, or Einstein-Rosen bridges, where a black hole on one side of the universe could be connected to a white hole on the other, creating a tunnel through space-time itself. Though no such structure has been observed, it remains one of the most fascinating possibilities in theoretical physics. If white holes truly exist, they could offer profound answers about the nature of time, information, and the birth of the universe. Some theories even suggest that the Big Bang itself might have been a white hole, a single, massive outburst of energy and matter exploding from a singularity, giving rise to everything we see today. In this view, our entire universe could be the interior of a white hole, born from another universe's black hole collapse. Whether real or not, white holes embody one of the universe's most beautiful symmetries. That every beginning may be an end seen from another side, and that even in the eternal darkness of space, there may exist places where creation bursts outward from the heart of destruction,